Good day, everyone. I am Balyonelo P. Berendes. Then, for today's topic, I am going to report or to talk about open integration formulas and multiple integrals. So, for the motivation, in numerical analysis, the Newton Cotes formulas, also called Newton Cotes quadrature rules, or simply Newton Cotes rules, are a group of formulas for numerical integration. So, based on evaluating the integrand at equally spaced points, they are named after Isaac Newton and Roger Cotes. So, the Newton Cotes formulas can be useful if the value of integrand at equally spaced point is given. If it is possible to change the points at which the integrand is evaluated, then other methods such as Gaussian quadrature and Clinsow-Curtis quadrature are probably more suitable. So, in Newton-Cotes formulas, we have here one topic of open integration formulas. So, actually, closed and open forms of Newton-Cotes formulas are available. So, we have closed, and for now, we have open available forms. So in the closed forms are those where the data points at the beginning and the end of the limits of integration are known. So as you can see in the figure 21.3a in the right side, the limits or the dots there is exactly at the beginning or the beginning of the what you call that in the alphabet in the letter A line and at the end. So the forms have integration limits, or the open forms rather, have the integration limits that extend beyond the range of the data. So the other side or other graph is the open forms. So the limit there is not starting at the beginning of the say the data or the shape. It's not in the beginning. So in the middle or actually, all in all, or in general, not in the beginning for the open forms. So, open Newton codes formulas are not generally used for definite integration. So, in several, in several references in internets, Google, even the YouTube, uh, the open Newton codes formulas is not often discussed or designed or interpret in doing a solution or getting a solution for problem. So normally they use loose forms. However, they are utilized for evaluating improper integrals and for the solution of ODE or ordinary differential equations. So not often familiar or not often used rather the open integration formulas. So in the Newton codes open integration formulas, so we have this introduced five formulas. No? Formulas are presented in the format kani nga this format so that the weighting the data points estimate the average height is apparent. So the step size is given by h, or the height is simply equal to b minus a all over n. So in summaries, kaning nga table, this table, the Newton codes open integration formulas, the formulas are expressed in the form of following equation. No? So as we can see, for example, in the points column, so we have there 1, 2, 3, 4, 5, or if the given points are in mid, in the same number. So in his in the perpendicular area, that is the formula that we're going to be used. For example, we have given 1 point. So 1 point is, as we understand, that is the midpoint. So we can use the formula b minus a function of x sub 1. So the truncation error, so we have there 1/3 times h, or the height, the power of cube, power of 3 function of element, giving element. So that is the formula. Then so on and so forth. If what is the given points, or how many given points are given. So for the discussion, so the open formulas are not often used, as I mentioned, not often used for definite integration. However, as discussed for the next following topics in integration of equations, they have utility for analyzing improper integrals. So in addition, they will have relevance to our discussion of multi-steps methods for solving ODE in steepness and multi-steps method. So as I research or getting a few inputs of this topic, so there's such a few that I can see that all in all, the keeping say that this method is not often used. Normally, the clause one is more simpler, but they said also that the open forms is more accurate over compared to close. Uh, so next is we have these multiple integrals. So the word multiple integrals. So these are widely used in engineering. So multiple integrals or multiple or more than two integrals we had in the equation, in one equation. For example, a general solution to compute the average of two-dimensional function can be written as have their f bar is equal to integral from limit c to d multiply integral second integral from a to b function of x and y dx multiplied by df dy all over d minus c multiplied by b minus a. So clearly the numerator there is called double integral since we have their double integration. So as mentioned, or that mentioned, the techniques discussed in this chapter can be really employed to evaluate multiple integrals. So a simple example would be take the double integral of the function over a rectangular area with a figure 21.16 in the right figure. So for this example, let's take one by one for the first integral and second integral. So first is the integral we have there from C in vertex, almost in the vertex, sa C to D is our first limit of our first equation. So let's say that this rectangular area is not perfect line or straight line. So maybe it's curved. So in order to get the value of that area side, the one of the formula that you can use is the integration or the equation using integration. So we have equation for the line or the curve rather, then do the limit c and d, then we can multiply it by another equation from limit or integration from limit a to b in different integration. So we can able to solve the area of not perfect or linear line. So we can recall from our calculus that such integrals can be computed as iterated integrals. So the formula, thus the integral is one of the dimension is evaluated first. So the result of the first integration is integrated in the second dimension. So it states that the order of integration is not important. A numerical double integral would be based on the same idea. First methods like the multiple segment trapezoidal or Simpson's rule would be applied in the first dimension with each value of the second dimension held constant. Then the method would be applied to integrate the second dimension. So in the formula, you can see that this two formula is equal. The two formulas or the two equation is this one. First is integral c from c to d times a to b function of x and y dx in dy. So is simply equal in from the integration of a to b times integral c to d. We only interchange for the two equations. We only interchange the first limit together with this um, constant. No, we just only interchange. So both in different manner or these two manners, this is are simply equal. No, so it doesn't matter as long as the limit is okay or right and equation is written accurately. So we have here example using double integral to determine average temperature. So for the example, suppose the temperature of a rectangular heated plate is described by the following function. So we have there function of T, temperature, function of temperature is x and y were equal to 2x and y plus 2x minus x squared minus 2y squared plus 72. So if the plate there is 8 meter long along the x dimension and 6 meter long or wide along y dimension, compute the average temperature. So first, let us merely use two segment application. So two segment of a trapezoidal rule in its dimension. So for the y and x. So the temperature at the necessary x and y values are depicted in the figure 21.17. So let's note that the simple average of these values is 47.33. So the simple average is adding all the values, then divide it by how many values we add. So that is a simple average, so we can able to solve or to get the value of 47.33. So the function can be also evaluated analytically. So we have different kinds of function there or steps there or methods that we can use in order to get the average temperature. So for the analytical yield or evaluated analytically, we can yield a result of 58.6667. So to make the same evaluation numerically, the trapezoidal rule is the first implemented along the x dimension for each y value. So uh, in order to get the value of the y, we will implement first a trapezoidal rule sa in the along x-axis. So 0 plus 40 plus 48. So take note that this is uh, trapezoidal rule. So meaning in along the middle, we will let's assume that in the middle we have 2 points there. 2 points or meaning 2 point the same points. So that is why we add 0 plus 2, 240. So 240 plus 48. So four values. So we come up to the value of 256. So these values are then integrated along the y. Each of the one of them, we get value 256, 496, 448. So in along the y dimension to give the final result of we have uh, 2,608. So take note also, even in the y-axis, we make or we have there imaginary the same 2 points in the middle. So based in the methods. So add it all, then assume that there are 2 points in the middle, the same value, then divide it by how many values we add. Then we get the value of 2,688. So, and dividing this by the area yields the average temperature as divide along the area sa area gitanan. So, natay value niya nga 2,608. So, the area there is 6 times 8 since 6 meter long sa Y, then 8 meter long sa X. So, we have value or to get a value of 56. So, we cannot apply a single segment Simpsons or one-third rule in the same function. So, we can able to apply the Simpsons one-third rule. So, this results in the integral of 2,816. So, an average value of 58.6667, which is exact. Huh? Why this is occur? Recall that in the previous topic sa Simpson one-third rule, yield perfect results for the cubic polynomials. So for the cubic DI, much better to use Simpson's one-third rule. More or less, but more or less the value is quite similar or no or the difference there is quite minimal only, no? But it is pointing along the or the correct answer. Since the highest order term in the Simpsons rule, since the highest order term in the function is second order, the same exact result occur for the present case. So in higher order algebraic functions as well as transcendental functions, it would be necessary to use multi-segment multiplication applications to attain accurate integral estimates. So in addition, so in the next chapters introduces techniques or they are introducing techniques that are more efficient than the Newton codes formulas for evaluating integrals of given functions. So this often provide a superior means to implement the numerical integration for multiple integrals. So that is the end of my presentation. Thank you for listening and have a good day ahead.